Okay, it's time. All right, shall we go through it real quick? This one shouldn't take too long. Basic substitution is what this is testing you on. Make sure you understand the concept. You're looking for something in its derivative. We all know that the derivative of e to the x is itself. And so maybe we can pick e to the x here is u. But you could probably go a little bit further. You could pick the whole thing. 1 plus e to the x is your u. If you do that, then the derivative of this will be just derivative here, which is just e to the x dx. So then you go looking, do you have that up there? Yes, right? This is the same expression, right? Just slide that e to the x back here. So you actually have e to the x dx right there. So that's going to be replaced with du. What's underneath the root will be replaced with u. And so this is just straight away to square root of u, du. And then you can just apply the power rule. So square root of u is the same as u to what power? U to the 1/2. So this whole thing becomes u to the 1/2 du. And then you go ahead and take the antiderivative. You add 1 to this. That's 3/2, right? And then you go 1 over 3/2, which is 2/3 plus c. And then you replace your u with this, and you're done. So your final result should look like this. 2/3, 1 plus e to the x to the 3/2 plus some constant. That's it right there. Okay? All right, now a couple of other things I wanted to mention to you. I have begun to, I sent an email out about this, I think on Friday or something. Excuse me. I've begun to create the solutions to all your homework sets in a video format. So like I did your homework for substitution, I did the entire homework set. It took me like 2 or 3 hours. And I did it on a board like this, and you can go watch it. So I'm going to try and continue to do that for the rest of the semester. Just be aware that if you go to Canvas, I think I put a link right on our homepage. It's in the email that I sent to you, but it's also, I think, linked in the Canvas page. Yes?
Is it on your YouTube channel?
It's also on the YouTube channel. It's a different playlist. It's 2414 Homework Solutions playlist. So I've started working on tonight's homework, and I hope to have that finished by tomorrow. I've actually done the first 20 problems, and they're ready on the web, so you can go watch those. All right? Any questions over homework? Yes? Number 33 on the substitution 5.5. So is there anything in particular on that problem?
On the video, you put 1/2 du.
Uh-huh.
When you put in the integral, it wasn't on the.
I didn't put it out there,
Yeah.
so I messed up? Okay. I might have messed that up. I did them really quick. It was Friday, and I have not checked them for errors, but we're all humans, so we're going to make mistakes. But I'll work it for real. I mean, I'll do it just to clarify it, okay? On this one was something I had not shown you in class. So this is actually a really good problem. Here, if we choose our u to be the 2x plus 5, then the derivative of that is just 2. I don't have a 2. I actually have another x out here, so that causes an issue. But it still works. All right, so we write 2x plus 5 over here. The derivative of this is 2 dx. And then this is where I have dx, right? I have dx. So I can just divide by 2. And I guess this is what I left out at some point. I left that out. Okay. Maybe. We'll see. So the dx will be replaced with this. This will be replaced with u. So I'll have u to the 8th. This will be 1/2 du, but what's the x? That still has to be resolved. So for those of you who watched the video, and what do I do to get this out of here? Take this equation right here and solve it for x. If you do that, then you'll get this in terms of u. So I subtract 5 from both sides here. And then I scale this by 1/2 on both sides. So half of this is x. And then half over here, I don't remember how I did it in the video. I might have left the 1/2 on the outside, I'm not sure. But so multiply both sides by 1/2 and I'm here. And so at this point I can rewrite this integral. And I think this is probably where I messed it up. The x here is going to be replaced with what? This right here, 1/2 u minus 5. This right here is replaced with what? U, so u to the 8th. And then dx should be replaced with 1/2 du. Is that where I left out the 1/2? Okay. This would be 1/2 du. So it'll be a 1/4 on the outside. I may have left it off. And then what's nice about this is that if I rewrite that 1/4 integral, I have, what, u minus 5 times u to the 8th. I can distribute that through. And that'll just get me u to the 9th minus 5u to the 8th du. And then you can just use power rule on that. So you'll have 1/4. Okay, what is the antiderivative of u to the 9th? 1/10 u to the 10th. Antiderivative of u to the 8th is 1/9 u to the 9th. But there's a 5 minus 5, so 5/9 u to the 9th plus c. And then you distribute a 1/4 through. And I guess I just did a 1/2 through or something. Okay. So your final result, final result, will be, let's see, 1/40th. And then what was u? 2x plus 5, all to the 10th. And then 1/4 times 5/9, negative 5, what is that, 36ths? 2x plus 5 to the 9 plus c. So look, if you find any more errors, please point those out. And what I'd like for you to do is just write your name down on a piece of paper for me and turn it in, and I'll consider that as bonus. All right? Will you do that for me?
Oh, no.
Yeah, just before the class is over, just make sure. That way, because I don't want to go back and watch these videos to check them for, little errors. But if you find something that's obvious like that, then, saves me the time of having to go back through everything. As I'm not using the key. I have the solutions, but I'm not even looking at them. I'm just working them out the way that you would. So, like I said, mistakes can happen. Except I already went and took this class and already got my grade, so you're the one who's getting graded on it. I mean, what would happen if you left something like that out on a test, right? What if you missed the 1/2? I mean, if the problems were 10 points, you'd get 9 of the 10. It's still, it wouldn't be catastrophic for me. The method is the more important thing. So as long as you're showing your work and I can keep up with what you're doing, then, no worries.
I have a quick question.
Yes.
For 28, it
Uh-huh.
was 2 to the t
Yes.
over 2 to the t plus 3.
Uh-huh.
I tried solving it, it just got a little ugly.
So the substitution on that is to take the whole denominator and let that be u. So u is 2 to the t plus 3. And you'll have to go back, and in the video that I did, you can go back and watch. I did a little review of what the derivative of 2 to the t is.
Okay.
What is the derivative of 2 to the t? 2 to the t times natural log of 2. So then you're off by a constant, and you can work it out, because the numerator on that problem has 2 to the t in it.
Okay.
Okay? All right, so today, integration by parts. We finished up last time, and I kind of rushed at the end through integration by parts, right? I'm going to put the formula, let's see where I'll put the formula. I'll put it on the board right here, even though it won't come out on the video. I thought about having a quiz today where I asked you for the formula, okay? And then I was also going to ask you to explain what it is that is useful about this formula. Like, what is the integration by parts formula all about? So can anyone tell me what it's about? Like, if you could summarize it in like one sentence.
You're making it easy.
Transferring the derivative. That's what you're doing. You're taking, that's what I said it is. Okay, some other people would argue it's something else. But I said what you're doing is you're transferring the derivative from one of your factors to the other. So the important thing in the formula is to understand you have two things being multiplied. They are totally unrelated to each other. And that's something that's different. With substitution, which is what the quiz was over, we were looking for something and its derivative, right? And they were connected to each other. One of them was the thing we were going to call u, and then its derivative had to be there also. In the integration by parts, these two things can be completely unrelated to each other. But one of them we need to be able to take the derivative of, and the other one we need to be able to integrate. And if we can do that, that new integral might be better than the one we started with. All right? So here we go. I have, if you look at the notes for this, right, then it's very short, okay? And then I have, let's see, problems, see, A, B, C, D, E, and F. And it's probably going to take me the majority of the class to go through those examples. I did, like I said, I did the homework problems. I did 20 of them. It took me about 2 hours to do 20 problems. So these can start to ruin your weekends. All right? All right, so example A. We want to find the antiderivative of x sine. Oh, you know what? Before I start this, I wanted to show y'all something really useful, okay? I'll get back to this. Okay. What is the integral of a linear expression like this? Okay, so here A and B are constants. C is your variable. What is the antiderivative of a linear expression like this? Ax squared plus bx plus c. So this would be antiderivative of ax. The a stays, right? Antiderivative of x is 1/2 x squared. Antiderivative of b is, and then you have a constant of integration, right? Yes? Okay. So a linear expression by itself, the antiderivative is just power rule, isn't it? Just power rule. There's nothing special here. But let's see what happens if we take a linear expression and we put it into another function and see how the antiderivative looks. So I'm going to take that same expression, but instead of it being by itself, I'm going to throw it into something, another function. So here, take a look at this. How about if I do, what's the antiderivative of cosine of ax plus b dx? So we all know, right? We all know that we can find the antiderivative of cosine by itself. But this in here is a little more complicated than just x. It's a linear expression in x. So what we could do is start the problem off with a basic substitution, a u substitution, and let the entire linear expression that's inside of the cosine be our u. What's the derivative of this? A dx, right? Just the number in front of x is our derivative. Do we have a dx in this expression? No, we just have the dx, right? So we would have to divide through both sides here, right? Divide by a. Or in other words, scale by a, like this. Yeah? And so when I rewrite this integral, it's now going to become cosine what? U, cosine U, times the dx is actually 1 over a du. And then what can I do with that 1 over a? Pop it out, right? So 1 over a and then du. Now, what's the antiderivative of cosine u? Other way around. Sine u, right? Sine u. So this would just become 1 over a sine of u, but u is ax plus b, plus some constant. Do you see that? So I think most of you at the beginning would have said, hey, the antiderivative of cosine is sine, right? So it would have been nice if the answer to this would have just been sine of this, right? It almost is. What's the only thing that's different? The 1 over a. That's always going to happen if this is a linear expression. You'll always have to scale out the number in front of x. I'll show you another example. And the reason I'm doing this is because it's going to pop up a lot throughout today, and I'm not going to spend time doing this. I'm not going to be like, oh, we make a substitution and we do this. I'm just going to say, this becomes this, and I'm not going to talk about it. Just going to go directly to it. So let's do another one which would be similar to this. Okay, how about this one? Integral. All right, I'll stick with the trig one for now. Let's see if we can do this with using the same logic behind this without having to do the whole substitution. U equals this, blah, blah, blah. So do you know what the antiderivative of secant squared is? What is it? Tangent, right? So this should be tangent of what's in there, right? Plus a constant. But because this was a linear expression, what's the number that was in front of x? 5. I know I'm going to definitely have to scale it by 5. And you can check it yourself. Take the derivative of this. What's the derivative of this? Well, secant squared of this, right? Times the derivative of what's inside. What's the derivative of what's inside? 5. Well, I just killed off the 5. So that 1/5 will always kill off that chain rule when you take the derivative. That make sense? Okay. Let's try another one. E to the negative theta d theta. So what you have to ask yourself is this thing in here linear? Okay. Was the thing inside here linear? What do we call the thing inside the function? It's the function's. That's the whole thing inside here. I'm saying if you just have a function, the thing inside of it, it's called, I think I heard it, argument. It's called the argument of the function. It's the thing that's being plugged in. So if you have like sine of theta, theta is the argument. If you have sine of theta plus 2 is the argument. So in this particular problem, the argument was linear, wasn't it? So I know I have to scale by the number in front of the variable. Here is the argument of this function linear. So what's the argument here? Negative theta. Is that linear? If the theta is messing you up, just make it an x. Is this a linear expression in the variable x? Yes. It's what? Negative 1 times x plus nothing. Right? It's like a number in front of x and then a number by itself. But the number by itself here is 0, isn't it? So this is a linear, the argument is linear. So the antiderivative of this should be what? What's the antiderivative of e to something? Itself plus c, but then I have to scale by 1 over a. And in this case, that would be 1 over what? Negative 1. That's the negative 1 that's in front of the variable, which is really just what? Negative e to the negative theta. The harder way to do this is to actually go and make a substitution. U is this, then write du is this, and then do all your substitution. But that could require an extra 5 minutes, and we don't have time. for that, do we? What? Yeah, shortcuts are good. You just have to remember, this only works for linear expressions, though. If the argument's not linear, chunk it. You can't use it. One more.
Does it work if you have like an extra like power t?
Up here, like if this were theta squared?
Yeah, theta like 2x squared.
No, if that's squared, no go. No go. In fact, if you do this and put a squared on it, that's an example of a function that cannot be integrated by any technique we ever learn in this class. But we'll learn in Chapter 8 there's a way to approximate this as closely as possible, as close as we actually ever need to get using power series. So there's a way to attack it, but no technique that we learn is ever going to be able to do it. Okay, so how about this? Last one. So I'm hoping that when you look at that, you say, okay, I've got 1 over a linear expression, right? 1 over a linear expression. So this is like a 1 over u. Do you know the antiderivative of 1 over u? Natural log, right? So this is probably natural log of 4x plus 1 plus a constant. However, the 4 was my a. And so I need to put a 1/4 in here. And you can check it, take the derivative, you'll get this back. One more, I said that was the last one. I'm going to tweak that one just a little bit because this is a common mistake I see. If I change that to a squared, can you say it's natural log anymore? No. But that looks like what? 1 over u squared, right? Which is u to the negative 2. So the antiderivative of u to the negative 2 should be negative u to the negative 1. So this should probably come out to be negative u to the negative 1 plus a constant. That's what it should. But I had the a, right? So what should I throw out here? Negative, well, it's a negative, so, and then I throw the 1/4. So here I'm going to go 4th, negative there, right? That should be the derivative of this. Could we check it real quick? This comes out, right? That becomes a what? Positive 1/4. Okay. Then this raised to what power? Negative 2. Then the derivative of the inside, which is 4. The 1/4 out front and the 4 cancel. And all you're left with is this to the negative 2, which is this. I think I told you that, the Cal 2 is dependent upon your ability to take derivatives. If it's still hard to see derivatives, it's very difficult to go backwards. All right, now we can begin today's stuff. So, part A. And it was x sine 10x dx. So someone tell me what's wrong with this, okay? I'm about to put something up here. I don't suggest writing this down. But someone tell me what's wrong with this. Or what I did. Someone tell me what I did and then tell me what's wrong with it. Anyone want to volunteer? What I did and why it's incorrect?
You look at each separately.
I did each one separately? So I said antiderivative of x is 1/2 x squared. And then the antiderivative of sine of 10x is what I just showed you, right? This is a linear argument. Antiderivative of sine is negative cosine. So you have the negative cosine, here's the negative, and then I had to scale by 10, and there it is, and I'm done. But the major problem with that is that you cannot undo a product this easily. That's the big no-no. So we have to have a way of doing it, and integration by parts is an approach. It's a tactic. It's a technique. But this is completely wrong. That gets you like 0 points out of 10 if you do something like that. All right, so if I'm going to use integration by parts, we have to keep in mind that integration by parts is going to be the next procedure that we're trying after we try substitution, right? Substitution should always be the first thing you go for. Do you see something and its derivative? So I see 10x. What's the derivative of 10x? 10. So then I don't have the x, do I? So maybe I could do what I did in that problem that I messed up on earlier. Maybe that'll work, but you can try it. It's not going to. You can go and do it. It won't work. So I don't see anything that's going to be a basic substitution. So my next tool that I pull out is the integration by parts, which means I have to identify one of these as being my u and one of them as being my dv. And I'm free to do that however I want, keeping in mind that it's all about the transferring of the derivative. Whatever you choose to be u, in the new integral it becomes what? Its derivative. And whatever you choose to be dv, in the new integral it becomes v. So one of them you have to be able to differentiate, the other one you have to integrate, right? So which one of these would become nicer or cleaner or better if I differentiate it? Which of this? Just that x by itself, right? Because derivative of x would be 1. And that would appear in my new integral, a 1. I love 1s, right? They don't mess anything up. But if I do that, then that's going to force me to use the rest of this as my dv, my dv, which means I'm going to have to be able to integrate that. Can you integrate that without the x? Yes. So once you choose your u, everything else that you see is the dv. And this is where I said I like to make a table, right? And different instructors have different ways. This is just the way I like to do it. So I always write down these two pieces of information first. I make my choice of u, which in this case would be what? We said x, and that forces everything else in there to be my dv. Don't forget the dx. Okay, that has to come. Now in this table, the reason why I put this one up here is because anything in the top row is the function, anything in the bottom row is its derivative. So going down, I have to take a derivative. The derivative of u is 1 dx. Don't forget, why do I put dx here? Because it's a placeholder. It's going to keep track of my variable. So, this is really a 1. I'm not going to write it, 1 dx. Now integrate this up, Sean. Put you on the spot, Sean. What do you think? I'll give you a hint. Okay, negative. I hear your cosine, 10x. I agree with that. There's one more thing. 1 over 10. Good. Okay, so that comes directly off of what I was just saying a minute ago. If we have a trig function, the argument is linear. When we go back up, we just do the normal antiderivative. We scale it by the 10. The reason it's negative is because the antiderivative sign is negative cosine. Y'all with me? Okay, so now we just use the formula. Ultraviolet minus voodoo, right? Ultraviolet minus integral voodoo. So ultraviolet are these two multiplied, the u times the v. And I'm going to put it in kind of a standard order. We like to put numbers out front, right? Negative 1/10. I have an x also, so I'm going to put the x next. And then I'll put the trig function at the back, cosine 10x. Everyone agree that that's u times v? This is u times v in no particular order, right? I just kind of, because it's multiplication, I just kind of mixed them up. And then the next thing, minus integral. So minus integral. And I get into a habit of leaving a little space in front of the integral because I may pull a constant out here. So you might want to do that also. Now, the next part of this is voodoo, right? Which will always be these two multiplied diagonally. And what we're hoping for is that this integral is better than the one we started with. So let's see. This right here times what? 1 dx, right? What can I do with the negative 1/10? I can bring it out of the integral, can't I? Now, is it okay with you if I do that all right now, or would you like to see it like negative 1/10 in here first? Bring it out. So what's it going to come out as? It'll change this to a plus. Plus 1/10. And then what else is in there? Cosine 10x dx. That's it, right? Now, isn't that an integral that you can handle? See, we've changed it. It started as this, right? But we've transformed it into a new integral where that x no longer appears because we transferred the derivative. Took the derivative of this, integrated that. Do y'all see it? And now, this is what we just did. So let's see. Reuben. See, I feel like I'm picking on the same people. I don't know why, but it seems that way. Reuben, I just want the antiderivative of this. Don't worry about the 1/10 in front. Just what's the antiderivative of that?
110 sine.
Yep, that's it. Plus c. I'm out of space here. All right, so I'll put it all together and we'll have our final answer. So this equals negative 1/10 x cosine 10x plus what? 1/100th? Right, 1/10 times 1/10? Sine 10x plus c. Box it up, that's your answer. Now look, I think we need to get some appreciation for what we've done here, all right? This integral, right, this integrand doesn't look that bad, right? I mean, x times a trig function, right? X times sine. Finding the derivative in Cal 1, right? Take the derivative of that, you would just do product rule and no one would be too freaked out about that, right? But going backwards in Cal 2, to go back to, where this came from, the derivative of what gives you this is that. That's much more difficult to see, right? I mean, nobody that I've ever met can just look at that and be like, sure, that's 1/10 x times, just no one I know that can do that. Other than Wolfram Alpha, right? So can we appreciate the complexity of this? If you took the derivative of this, you would get this. But think about what it would take to check. You do product rule on these, right? There's some chain rule involved there, and then derivative over here. And when you put it all together, this is all that should be left. Things are going to cancel, and it'll work. You just have to check it. Questions?
So once you have the left side done, the sign will change.
Pardon me?
Once you have the left side done, the sign will change.
How do you mean?
Like once you put U and V together.
Once you know how we had this integral here?
Yeah.
Once you integrate that, you're done. Because now you have that your integral equals a bunch of functions with no more integral sign in it. So the integration by parts is a transferring of the derivative in the hope that the new integral is doable. Right. In my examples, if you looked at your notes, I called part A, example A basic substitution. A basic integration by parts. B is what I call a not so obvious integration by parts. So what I'm trying to do in these examples is give you a good mixture of the different types of things that you could be faced with when it comes to integration by parts. So this one, not so obvious. How about just a basic, basic substitution, what you were quizzed over today before we came in? Like, do you see something in its derivative? Do you know the antiderivative of arc sine? No. You know the derivative of arc sine, because we did that when we first started. But you don't know the antiderivative of it. So there's nothing basic we can do about it. No basic substitution, no basic formula off our formula sheet. The only other thing we have is integration by parts. But what's wrong with this? I mean, why is this not looking like integration by parts should be used? Anyone want to tell me what?
There's no x in front of the arc sign?
Okay, there's no x, but in other words, there's only one thing, right? Like in integration by parts, I said there's like two things, right? There's two things here. There's one that's going to be your u and one that's going to be your dv. You could argue with me right now that that's just one thing, right? But it actually is two things because there's multiplication here, right? So one thing you have is the arc sine of pi x. The other thing you have is dx. So there are two things there, right? One of these I need to choose to be my u, and one needs to be my dv. So let's think about the wrong way first. If that's my u, what's the derivative of that? What's the derivative? If this is my u, right? In my new formula, it's going to be the derivative of that. So what's the derivative of the derivative? It would be the second derivative, wouldn't it be? And that is going to create all sorts of chaos. So you don't ever, this is good news, you don't ever want to choose dx as your u, ever. Dx can be your dv, but it can't be your u. So if that can't be u, the only other choice for you is what? This. But do you see how this is different than the previous problem in the sense that in the previous problem, was it sine? Wasn't it somewhat obvious that if I choose this for u, it gets better? Yes? It gets better when I take its derivative? Do you all agree that if I choose this to be u, its derivative is nothing nice? Like I don't really appreciate that that got better? Do you understand? But it's really my only choice. And that's why I'm calling this the not so obvious integration by parts. Because it's not obvious that this should be even integration by parts to begin with, and then that the best thing to choose is, for you is this. You with me? Okay, but let's just see what happens. Sometimes you actually have to run a marathon to know what it's like to run a marathon, right? I mean, like you actually have to do it. I watched Good Will Hunting the other day. Every once in a while I'll pop that video in. And there's a scene, I don't know if you remember, how many of you have seen Good Will Hunting? You know what I'm talking about. Okay, so the genius kid who's Matt Damon, he's arguing with the psychologist, and the psychologist takes him out to a pond, and they're sitting there talking, and he says, you know, you're so bright, you know, you could tell me anything about all these different books you've read, but you've never actually like seen the Sistine Chapel. You don't know what it smells like in there, like you haven't experienced it. It's kind of the same thing here, if I can make an analogy. It's one thing to just watch someone do something and be like, got it, got it, got it. Until you actually get in there and do it, you're really not getting the full experience of it. So you have to try these things. Pick that to be you. Why? Because you just don't really have any other choices. And see what happens. Hope for the best. Now, let's see how many of you can see this. Do you see what this turns into? Do you know what that turns into? The derivative of that? 1 over square root of 1 minus x squared. That's the derivative of this. So I'm going to have that in my new integral. Oh, not happy about that, right? You see that's but okay, there's that, and then this one had to force to be what we said? Dx. So that's it. Now we just work with this derivative down, integral up. So derivative down here, du is, be very careful here because we have a pi x inside. So derivative of arc sine of something is 1 over the square root of 1 minus the argument squared. Pi x squared. Can I do it this way? Pi squared x squared. I went ahead and squared them both. Because it's pi x, that quantity squared, which is the same as squaring the pi and squaring the x. Am I done? Now the derivative, what's inside? Pi. And then what do we always throw on the end of this? Nope, you're integrating. Times dx, or just dx. So we have to make sure, because we came down, took the derivative, we always have to have that differential dx sitting out there. Do y'all see this? Okay, the other side, go up. It's the antiderivative of 1. In this case, just x, right? Because the variable's x. Go up, it's x. Questions? No? Let's see. Alejandro? I don't think I call on you much. Maybe I do. I just want you to tell me what ultraviolet minus voodoo is going to look like up here. So what?
So x and sine inverse of pi x.
Okay.
And then
What about the sign here after this? After your sine inverse of pi x, what do you want me to put here?
Oh, dx?
No, you have ultraviolet, right? And then minus, right? Minus.
Oh, yeah, minus.
Okay, minus the integral, that's all. And then let's do voodoo. So you got to multiply this times this, right? So where's that x going to appear? Up top, right? With the pi, right? So I could put pi x over square root 1 minus pi squared x squared dx. With me? Any questions? Vanessa? Any ideas? This looks pretty bad, right? Okay, so you start over with the first thing that we talked about, basic substitution. Do you see something and its derivative? What?
The 1 minus pi squared x.
The whole thing under here? Everything here? Call that u? Okay? 1 minus pi squared x squared. What's the derivative of this? So derivative of 1 is 0. Minus pi squared is a constant, right? So what's derivative of x squared? 2x. But I have a pi squared there and a negative. So I could put what? Negative 2 pi squared x dx. That would be my du, wouldn't it? Do you have that somewhere? Almost, right? Almost. What do you have? What we do have is this. Pi x dx, right? Pi x dx. Well, I have two factors of pi. I have pi squared, so I can just peel one off. I do have a pi x dx, don't I? But I also have the negative 2 and an extra pi. So how can I resolve the negative 2 and the extra pi that's there? Divide both sides by pi and 2 and negative. There. If I do that, then this, right, I divided by negative 2, it's gone. Divide that by pi, it's just pi x dx. And this matches exactly with what we have up there, isn't it? All right, so just a little recap, we're not done. We start off the problem by doing integration by parts. That creates a new integral. I didn't have many choices. I had to do this is my only real option. When I got to this, I was a little bit terrified when I first saw it, but then I realized it was just a basic substitution. So this is a new integral, right? The u that I'm looking at here is not this u anymore. This u is just to get me to that new integral. So now this one, I'm going to look at this integral, and I'm just going to be looking here, okay? And I'm going to do that right here. All right, I'm just going to finish that, what's in the brackets right here. What's in the brackets becomes what? Integral. So all this is going to be part of this, right? So I have a 1 over what? 1 over root. What's all this junk? U. And then what does all the pi x dx turn into? This right here? So how about I put negative 1 over 2 pi out here, and then the du, I slap that on the back like this. Isn't this with the appropriate substitution? That's this. Which is negative 1 over 2 pi times 2 square roots of u plus c. So what did I do here? I integrated, right? This is really u to what power? Negative 1/2. You add 1 to that, it's what? 1/2, and then you multiply by 1 over 1/2 is 2. So I'm doing all of that mentally now because that was 2 classes ago. So this, from here to here, should be something you should do. I'm not saying you should be able to do it mentally. I'm just saying you should be able to handle that at this point. Okay?
I was wondering where that 2 came from.
What 2? This one?
Yeah.
That's the power rule. Because when you add, that's what I'm saying, when you add 1 to this power, you get 1/2, but you always have to scale by 1 over that 1/2, which flips to become a 2.
Got it.
So these 2's cancel. And this becomes -1 over pi, what, square root of, what was u? All that, right? So 1 minus pi squared x squared plus c. So everything in this bracket becomes this right here. And there's no more integral sign, so we're done. But I'm going to write the whole answer out now, because that's not our answer, right? It's this part, ultraviolet, minus that part. Okay? So the final result, if I replace this in the bracket, if I replace that with this, plus c, I'm going to throw a c way out here. Yeah, the negative is going to become positive now, right? And then that's when I'll write my final answer. So x, arc sine, pi x, plus 1 over pi, square root, 1 minus pi squared x squared plus a constant of integration. And we're done. So the most critical part of this so far is getting that u correct, right? In the beginning, once you get that into the table, then everything else should flow pretty nicely. But that's the challenge. Are you ready to see another one? Of course you are. Yes? Real excited about it? What are y'all thinking so far? I mean, what's your initial reaction so far to this method? Yeah, practice. Yeah, it definitely is. Oh, yeah. All right, in this example, this thing right here is beta. And we're just going to say beta is a constant. It may as well be the number 5, right? It's just some number that we don't know. But it's not the variable in the problem. The variable in the problem is t. And that's indicated by the differential dt. So we have t squared cosine beta t dt. And so maybe we think, okay, is there a basic substitution? Not something basic, right? I don't see something in its derivative. Oh, wait, hold on. What's the derivative of t squared? 2t? Don't I have a t right in there? But what did I tell you about the derivative of this thing if you use basic substitution? Make sure it's not trapped inside of another function. In this case, the derivative of this is trapped in the cosine. You don't want that. You want it to be separated at the end of the day. You want it to be able to be factored out like that. So that wouldn't work. Integration by parts, I could choose one of these to be u and transfer the derivative. So I know that if I choose one of these to be u, in the new integral, its derivative will be there, right? So which of these would you like to choose to be u, and tell me why you'd like to choose it that way? You want to try t squared? Why? The derivative of this would be what? In the new integral, it would be what? Be 2t? But you still have a t there, right? And then what about this one? If this one is u, we know in the new integral it's going to be what we just said? I don't want to push too hard, but I really want you to start looking at it this way. Some teachers teach this in a more methodical way, which is, I don't even know the acronym. Has anyone ever heard there's like an acronym of which of these you should choose? It's like you always choose this first. If not that, then choose this, and if not that. It's like, I don't even know it. I never learned it. I don't like it. What is it? Yes. What is it? What are the letters?
L-I-A.
TE. This is like something some instructors teach. I'm not saying it's the wrong way to do it, but they say like, if you have something like this, always try and use the L, like a logarithm, and then what, the inverse function, and then I don't even know what all these stand for, but it's more of like, try that, then that, then that, then that, but there's no real like thinking of actually what you're trying to do. What you're trying to do here is make your new integral easier to handle, right? That's what you're trying to do. So to me, there's not enough thought in that. And remember, Cal 2 is not about can you integrate, it's can you think, right? You want to be an engineer, can you think in kind of foresee things? Is that possible? Does your brain work that way? So this to me is a bigger skill than anything else we're doing here. I'm thinking here mentally, that's what I'm doing in red, I'm thinking my new integral is going to have what in it? If I choose my u to be t squared, my new integral is going to be what? 2t, right? And then this one, the antiderivative will appear over there, which will have what in it? Like a sine, beta t, and then I've got to scale it, right? Because it was beta, and I'll have a 1 over beta I could plot. Maybe I don't see all that. But what I do see is I've got a 2t and a sine, right? Is that any better than this? I still have a t, don't I? But what's happened to it? It's no longer t squared, it's what? 2t. So why not then, when you get to this point, do integration by parts again? And if you did integration by parts again, this problem would become its own ultraviolet minus voodoo, and what would the new integral in this one become? What's the derivative of this? 2, right? And then antiderivative of this would be a cosine. That you can handle. Do you understand this? This is why in the example I say this is an example of repeated integration by parts. We're going to repeat the process twice because in order to get it down to something we can handle, we have to first reduce it from a t squared to a t, and then the next step will reduce the t to a number. Yes? No? Okay. In my opinion, that's more powerful than just try this first, then this, then that. All right. All right, so here we go. It's going to take a little while. Oh, and why didn't I choose this to be the u? What would this become if that were the u? Again, I'm thinking ahead in red here. If this were the u, what would my new integral in integration by parts become? I would have sine of something, right? Because I would be doing the derivative of cosine. It would be negative. But then I would have to do what with this? Integrate it. And that means I would have a t cubed appear over here. What's some numbers in here? What's better, this one or this one? Well, I've actually created more complexity, haven't I? I've increased the power on t as opposed to decreasing it. So that is definitely not the way I want to go. All right. All right, so the appropriate choice, u is t squared, dv is cosine beta t. I'm about to call on somebody, dt. Yo?
Yo-yo.
Yo-yo? No, it just says yo. It's yo! Okay, du, right? What's du here?
2t.
Yo? 2t
Times dx.
times d
X. Oh, d. T.
t.
Sorry.
Yep, oh, that's all right. And then keep going, yo.
Negative sine.
Careful. You're doing antiderivative, not
Oh.
derivative.
So it's sine.
Sine,
Of
beta,
t.
t. Now what's missing? There's something else. Remember, this is a linear expression in t.
Over beta.
Beta, there you go. Got it? Okay. So that's the proposed table for integration by parts. The rest of this will be plugging into the formula, ultraviolet minus integral voodoo. So ultraviolet, let's see. Kiki, are we talking still? Yeah, are we still talking from last class? I think I upset you. Are you?
I've been over that.
Oh, you're over. I'm kidding with you. Okay, so you want to go ahead and give me ultraviolet minus voodoo then? However you want it written.
P squared
Okay?
times 1 over beta.
Times 1 over beta
Sine B
sine beta t. Okay?
Oh, you want the rest of it?
Oh yeah.
Minus integral 1 over beta sine B beta t. And then T2.
2t
Yeah.
dt. Okay, so that's it. Just reading it pretty much right off the way it is. And that's fine. I mean, if that's the way you need to start this, that's great. Just write it all out. Then you might get into a habit of starting to like pull things out and clean things up and change the order. Are there any questions on that? Okay, so I am going to clean up a little bit here. 1 over beta is a number. So I like to always put my constants out front. 1 over beta. T squared sine beta t. Now here, are there any constants in here that I can pull out of this integral before I actually compute the integral? 2 and 1 over beta. So how about pulling out a 2 over beta integral? How about we put that t in front of the sign? Beta t dt. So remember that the goal of integration by parts was to transfer the derivative so as to create a new integral that we hope is better than the one we started with. So here's our original integral. We've got it down to this, and here's our new integral, but that new integral is still not doable as it stands. So I'm going to repeat integration by parts on that one integral. And when I do that, I'm going to put the integral in brackets like this, and I'm going to do it in red so that you at least know that I'm talking just about this for now, all right? So first let me do my table on the side, which will be here. I have a new table because it's a new integration by parts. What are we going to choose for u here? T. dv then by default has to be everything else that was there, which is sine beta t dt. Differentiate down, integrate up, right? du is dt. V is Ron.
It's going to be cosine.
Cosine.
And times
1 over.
beta.
One more thing. Negative. There we go. Just keeping the blood going there. So here to here, we're integrating up. Get to this. So just the part in red, right? Just the part in red is going to become a brand new ultraviolet minus voodoo right in here. And we still have a negative 2 beta in front of it all. So we've got to keep track of all that. So I'm going to put on the top here, I'll put it right here, I guess. Okay, so from this line, I'm going to go to my next line. It will be equal to 1 over beta. So this 1 over beta t squared sine beta t was the original u times v, right? Ultraviolet. Minus 2 over beta, and now here comes my second ultraviolet minus integral voodoo. So this time, ultraviolet here and here. So what? Negative 1 over beta